All right, guys, we're going to get started on Chapter 8. This is the first time we're looking at graphs of quadratic functions. So it should be interesting. You should be expecting to graph a lot. If you don't have a Desmos window open right now, maybe you want to pull that up right now, pause it, whatever you need to do. But I'm ready to go. I got my headband on. I've got my journal going. So I'm going to get started. All right, so graph each function, compare each with the graph of f of x equals x squared. So what we're meant to do is graph onto this axis, well, in this case, g of x equals x squared. So let's take a look at Desmos, and here we go. The red line that I have here, this red one, that is y equals, I forgot that I can't write on this. This right here is y equals x squared. The blue line that you see there is y equals 3x squared. Even more, let's take a look at this. Where do these lines hit the coordinate axis, as it will? Where does it hit a lattice point? So right here, that's certainly a lattice point. That's a lattice point at 1, 1. Okay. But the blue line has a lattice point as well right here, and that's at 1, 3. I don't know if you can see it. Yeah, 1, 3. Okay. So, where does that 3 come from? I wonder. Why is it this one 1? I'm going to put a 1 there. And why is this one 3? Do you think that's a pattern? You betcha. So over here, when I graph this, notice that here's that lattice point again, 1, 5, 1, 1, and negative 1, 1. Now I can put the lattice point here at 1, 3, and negative 1, 3. And this graph right here, I'm not going to do a very good job of it because, well, this isn't paper. Right, I'm sure you'll do a much better job than I will. But this graph right here is y equals 3x squared. So what do we notice? Well, it goes all the way down to the same point at the bottom. So the low point is the same. And then it's narrower. That 3 made it narrower. Let's take a look at letter B. You've got negative 5x squared. How is that going to look? And if you want a preview of what should be happening, take a look at the coordinate axis they gave you. A lot of times if you look at the question, you kind of know what to expect in the answer. But let's look at Desmos. Here's my Desmos. I've graphed that already. And look at that. If y equals x squared is the red line, y equals negative 5x squared is the blue line, and notice how it's reflected around the x-axis. It's going downward. Now let's find its lattice points. So, I'm having a hard time seeing, so I'm going to move it over here. Lattice points. Where is that cursor? Lattice points. Now I can't find lattice points again over here. That is at negative 1, negative 5. Over here, 1, negative 5. So when you trust me if I tell you that this number in front of x squared tells you where that lattice point is, 1, comma, negative 5. This is still y equals 1x squared. So this is still telling me that I have a lattice point at 1, 1. This one tells me I have a lattice point at negative 5. 1, negative 5. Going back to the graph here on my your journal, if I go to 1, I should plot this at negative 5, and I'm not sure where negative 5 should be. This is negative 8. This must be negative 6, so that must be negative 5 right there. So let's put a nice point there, nice and meaty. And this time, because that that's a negative 5 for a. And what I mean by a is y equals ax squared plus bx plus c. Because a is negative, this is heading downwards. And also, we know that that is where the lattice points should go. So for number C, that shouldn't be a surprise for us then. If we figured out the pattern, that's a negative 0.2, so I should have a lattice point at 1 and negative 0.2, which is probably right about here. And then negative 1, negative 0.2. So this is going to give me a parabola that looks like it's fatter. Okay, so fatter, opening downwards. This one over here, fatter still, it's 1/10. So this is going to open upwards, and it's fatter. Okay, so 1 and 1/10, man, that's like right here. And negative 1 and negative and 1/10. Sorry, negative 1 and 1/10. That's right there. So this is gonna, that's almost a line, right? Very shallow curve. And of course, it should be symmetric around the y-axis. Well, that leads us to question 2 now. What are some characteristics of the graph for the quadratic function f of x equals ax squared? Well, first of all, it's going to look like a parabola. That's what we call that shape. Second of all, A tells you the lattice point. So if A equals, let's say, negative 2, then lattice points are the x-coordinate of the lattice point is going to be 1, and the y-coordinate of that lattice point is going to be negative 2. And then on the other side, negative 1, negative 2. Okay? Moving on to 3. How does the value of A affect that graph? Use a graphing calculator to verify your answer. Luckily for us, I went ahead and put this on Desmos, and as I slide A, you should be able to see the effect that it has. So first of all, what if I make A big? What a surprise. We get narrower and narrower. The red curve is ax squared. All right, let's reset that. Here's at 1. Oh, that was at 1. And then now we're going to go backwards. What happens? Notice value of A is 0.6, 0.5, 0.4, 0.3, 0.2, 0.1. Those get fat. And then as we get to A equals 0, we just get a horizontal line. And then now A is negative, and then it gets more and more skinny in the negative direction. So take a look at how those numbers work. I'm going to slide this back and forth for a little while. Take a look at that, how that value of A affects the shape of the parabola. Right over here, things change really fast. Okay? Of course, back in the day, we just looked at that and said, well, that's going to be our lattice point. That's where that's going to go. So, back to our journal. How does that affect the graph of f of x equals ax squared? Well, it kind of controls two things. They're both related. Okay. So first of all, it affects the lattice point, which affects the thickness of the graph. Parabola. Okay. If A is between 0 and 1, let's write it the way they wrote it. If A is between 0 and 1, parabola is wider. And we shouldn't say thicker anymore, I don't think. It's wider then y equals x squared. If a is greater than 1, then the parabola is narrower than y equals x squared. So that y equals x squared, we call it the parent function because we compare all of the other parabolas to y equals x squared. How does y equals x squared change if we stick different numbers on it? Okay. Moving on, here we got figure shows a graph of a quadratic form y equals ax squared, which intervals describe the value of a. Well, let's see. Can I tell what the lattice point here is? I'm going to go ahead and zoom in right here. Okay, that didn't zoom, but this will. I'm going to zoom in right there. Okay. So can I tell what that lattice point is? Is that lattice point greater than 1 or less than 1? That looks like about 1 comma, I don't know, 0.2, maybe 0.3. So I would have to say that a is about equal to 0.3. Or another way of saying that is 0 is less than a is less than 1. That's what they really want. We have a value of a that is between 0 and 1. Also, don't forget that if a is negative, the rules are exactly the same, but instead our parabola is going to open downwards. So I don't know why I keep doing this shape. Maybe because it's fun, I don't know. Back to the math here. A quadratic function, parabola, looks like a U. That gets wider and wider. You know, I wrote that instead of typed it, and I'm learning that I should just type this stuff in here. Will that turn it? Yeah, that'll do it. Ooh. That didn't. Yeah, let's move that down. And I guess I should have just typed it all along. I'm going to fix that. So remember, when you draw your parabolas, the parabolas keep on getting wider. They don't just stop getting wider and all of a sudden they have sides that go straight up and down, okay? The vertex is the lowest point of a parabola that opens up. It's also the highest point of a parabola, not a parabola, that opens down. Okay, so we have downward opening parabolas and we have upward opening parabolas. Axis of symmetry, that is the line in the middle of the parabola. It is a line of reflection. So in other words, the left side of the parabola looks just like the right side of the parabola. Over here, notice that as we read the graph from left to right, which is how you should be reading the graph, we decrease until we get to the vertex. And then at the vertex, we have the axis of symmetry. The left side and the right side look the same. And then we start increasing once we move away from the vertex. So it goes down, and then it goes up. Okay. This over here is the vertex, that's at 0, 0. This, the axis of symmetry, if the vertex is 0, 0, then the axis of symmetry is x equals 0. And guess where that 0 comes from? Yeah, that just comes from the x-coordinate of the vertex. All right, let's do a few more of these. Actually, no, let's just go ahead and start doing these problems. I think we're good enough to go. I've given you so much incredible information already. So the first of all, identify the characteristics of this quadratic function and of its graph. Okay, there are only two. We're going to do a couple more. That's the vertex, the most important part of the parabola. This right here, if I can get a straight line, that's the axis of symmetry. Which is a lot to write, really. This is decreasing, and this right here is increasing. Let's do it again. Here's the vertex. This is the axis of symmetry. Try to write with a thicker line on this one. Axis of symmetry, AOS. That's what we do in calculus. This is increasing because it's going upwards. Increase. This is going downwards, so it's decrease. Remember, always read your graphs from left to right. More of these problems. Let's graph these guys. How about 5x squared? Okay, let's make a coordinate axis here. And I've told you so much about how to do these already. You know the vertex is at 0, 0 because the form is y equals ax squared. You know where those lattice points are. They're at 1, 5, 1, 2, 3, 4, 5, and negative 1, 5. Okay. With those 3 points, you can graph your parabola. Notice how my parabola gets wider and wider. It doesn't turn into a U with vertical sides. Let's take a look at this one. Mx equals negative 4x squared. And I don't know why I'm drawing my axes fuzzy like that. Whatever. This tells me that a equals negative 4, so I should have my lattice points at negative 4, 1, negative 4, 1, 2, 3, 4, and negative 1, negative 4. So here is the parabola. Okay, 3 points, go out and conquer the world. Moving on, negative x squared. Not even going to bother with that one. That one, negative 7x squared. That's just like negative 4x squared. Just the lattice points are going to be at negative 7. Ooh, this one's a challenge. How about negative 1/5? Okay, let's do negative 1/5. Here are my coordinate axes. Okay, and let's do this. Let's make this 1, negative 1, of course, and let's make this positive 1. That would make this negative 1 over here. So the lattice point is 1/5, and what is 1/5 of the decimal? Computer, what's 1 divided by 5? You totally ignored me. Computer, what's 1 divided by 5?
1 divided by 5 is 0.2.
Okay, so this is negative 0.2. It doesn't take a brain surgeon here. You know that that's less than 1. You know that it's negative, so you know it's opening downwards. You also know where that lattice point is. It's negative 1, negative 0.2, and positive 1, negative 0.2. Yes, it's the same thing as A. Graph it. Look at that. You know, some algebra students get a nightmare looking at that one, and you guys have it so easy. Okay, determine whether this statement is always, sometimes, or never true. The graph of a of x gets wider than the graph of f of x if a is equal to 0, if a is greater than 0. No, that's not true. Only if a is greater than 1 will it be wider. So it's sometimes true. It's not always true. Sometimes true. Okay, so it's wider if a is greater than 1. How about this one? The graph of ax squared is narrower if the absolute value of a is less than 1. And that's true. Absolute value of a is less than 1 means we get some kind of a fractional value. So this is always true. All right. And taking a look at number 10, maybe I should put these in absolute values because I don't know. Sometimes we're looking at parabolas that open downwards. All right, so 20 minutes up, 21 minutes. That was the best 21 minutes of algebra that you can have today. Have a good time and go forth, do your big ideas, okay? All right, see you next time, guys.